Welcome to this practice session on quantities and units in electrical engineering. In this first worked example, we examine the concept of quantity of electricity, also referred to as electric charge, and apply the fundamental relationship between charge, current, and time. The problem states, a current of 5 amperes flows for 2 minutes. We are required to find the quantity of electricity transferred. The governing formula is Q equals I times T, where Q represents charge in coulombs, I represents current in amperes, and T represents time in seconds. A critical step here is the unit conversion. The time is given as 2 minutes, which must be converted to seconds. Since there are 60 seconds in 1 minute, 2 minutes equals 120 seconds. Substituting the given values, Q equals 5 amperes times 120 seconds equals 600 coulombs. Take careful note of this unit conversion step. In engineering problems, quantities will frequently be presented in non-SI units, such as minutes, milliamperes, or kilonewtons. You must always convert to the base SI unit before substituting into any formula. The final answer is 600 coulombs. This slide presents a worked example on the topic of force. Recall Newton's second law of motion. Force equals mass multiplied by acceleration. This relationship is fundamental not only in mechanics, but also in electrical engineering, where forces act on conductors in magnetic fields, on charged particles, and on mechanical components of electrical machines. The problem states, a mass of 5,000 grams is accelerated at 2 meters per second squared. We are required to determine the force needed. Observe the unit conversion required here. The mass is given as 5,000 grams, not kilograms. In the SI system, the standard unit of mass is the kilogram. Therefore, 5,000 grams equals 5 kilograms. Applying Newton's second law, force equals 5 kilograms times 2 meters per square second equals 10 kilograms meter per square second. Since 1 Newton is defined as 1 kilogram meter per second squared, the answer is 10 newtons. The final answer is force equals 10N. Always verify your units at each step of a calculation. A common source of error in engineering problems is neglecting to convert quantities to SI units before substitution. This is the second worked example on force, involving the gravitational force acting on a suspended mass. The problem states, find the force acting vertically downwards on a mass of 200 grams attached to a wire. The force acting downwards on any mass near the Earth's surface is its weight, equal to mass multiplied by the acceleration due to gravity. The standard value of gravitational acceleration is g equals 9.81 meters per square second. The given values are mass equals 200 grams equals 0.2 kilograms, and g equals 9.81 meters per square second. Applying the formula, force equals 0.2 kilograms times 9.81 meters per square second equals 1.962 newtons. The final answer is 1.962 newtons. This example reinforces an important distinction. Weight and mass are not the same quantity. Mass is measured in kilograms and remains constant regardless of location. Weight is a force measured in newtons and depends on the local gravitational field. In electrical engineering, this distinction is particularly relevant when designing lifting mechanisms, relay armatures, and electromechanical actuators. This slide addresses two closely related quantities, work done and power. Work done is the product of force and displacement in the direction of that force. It is measured in joules, where 1 joule equals 1 newton meter. Power is the rate at which work is done, measured in watts, where 1 watt equals 1 joule per second. The problem states, a portable machine requires a force of 200 newtons to move it. The machine is moved 20 meters, and the movement takes 25 seconds. We are required to find the work done and the average power utilized. For work done, W equals F times D equals 200 newtons times 20 meters equals 4,000 Newton meters equals 4 kilojoules. For power, P equals W divided by T equals 4,000 joules divided by 25 seconds equals 160 joules per second equals 160 watts. The answers are work done equals 4 kilojoules and power equals 160 watts. In electrical engineering, understanding mechanical power is directly relevant to the rating of electric motors, which convert electrical energy into mechanical work. A motor rated at 160 watts would be required to perform this task continuously. This second worked example on work done and power involves lifting a mass against gravity, a scenario frequently encountered in the design of hoists, cranes, and lifting equipment in electrical engineering applications. The problem states a mass of 1,000 kilograms is raised through a height of 10 meters in 20 seconds. We are required to find both the work done and the power developed. Part A. Work done. To lift the mass, we must apply a force equal to its weight. The weight equals mass multiplied by gravitational acceleration. F equals 1,000 kilograms times 9.81 meters per square second equals 9,810 newtons. Work done equals force times distance equals 9810 newtons times 10 meters equals 98,100 Newton meters equals 98.1 kilojoules. Part B. Power developed. Power equals work done divided by time equals 98,100 joules per 20 seconds equals 4905 kilojoules per second equals 4905 watts, which is approximately 4.905 kilowatts. The answers are work done equals 98.1 kilojoules and power developed equals 4.905 kilowatts. This type of calculation is directly applicable to the specification and selection of electric motors for industrial lifting applications. An engineer would need to select a motor rated at no less than 4.905 kilowatts to perform this task, and in practice, a safety margin would be added. This slide presents a worked example on the determination of the total electric charge represented by a given number of electrons. The problem states how much charge is represented by 4,600 electrons. To solve this problem, we make use of a fundamental physical constant, the charge of a single electron. The electron carries a charge of negative 1.602 times 10 to the power of minus 19 coulombs. The negative sign signifies that the electron is a negatively charged particle. The total charge, Q, is obtained by multiplying the charge per electron by the total number of electrons. Q equals charge per electron times number of electrons. Q equals minus 1.602 times 10 to the power of minus 19c times 4,600. Q equals minus 7.369 times 10 to the power of minus 16c. The final answer is Q equals minus 7.369 times 10 to the power of minus 16c. Several important observations should be noted. First, the result carries a negative sign because electrons are negatively charged. Second, the magnitude of this charge is extremely small, of the order of femtocoulombs, which reflects the fact that the coulomb is a very large unit of charge relative to the charge carried by a single electron. For context, it takes approximately 6.24 times 10 to the power of 18 electrons to constitute a charge of 1 coulomb. Third, the technique of multiplying a charge per particle by a number of particles is directly applicable to both electrons and protons, as you will see in the next example. This worked example extends the concept of atomic charge to protons. The problem states, calculate the amount of charge represented by 10 billion protons. Protons carry a positive charge of equal magnitude to that of an electron. the charge of a single proton is E equals plus 1.6021 times 10 to the power of minus 19 C. Note the positive sign, which reflects the positive nature of the proton. The solution proceeds in 3 steps. Step 1. Identify the charge per proton as plus 1.6021 times 10 to the power of minus 19 C. Step 2. Express 10 billion in scientific notation. 10 billion equals 10 times 10 to the power of 9 equals 1 times 10 to the power of 10 protons. Step 3. Multiply charge per proton by the number of protons, applying the rule of indices for multiplication of powers of 10. Q equals 1.6021 times 10 to the power of minus 19 times 1 times 10 to the power of 10 equals 1.6021 times 10 to the power of minus 9 C. The final answer is Q equals 1.6021 times 10 to the power of minus 9 C, which may also be expressed as approximately 1.6 nanocoulombs. This problem illustrates 2 important skills: the conversion of a large number into scientific notation, and the multiplication of numbers expressed in scientific notation using the rule that the exponents are added. Both of these skills are applied extensively in electrical engineering calculations. This worked example introduces the relationship between electric charge and electric current, expressed through the differential form of the definition of current. I equals dq divided by dt. This equation states that the instantaneous current at any point in time is equal to the rate of change of charge with respect to time. This is the fundamental definition of electric current, and it forms the basis for all subsequent analysis of time-varying electrical quantities. The problem states the total charge entering a terminal is given by Q equals 5t sine 4 pi t millicoulombs. Calculate the current at t equals 0.5 seconds. Step 1. Differentiate Q with respect to t using the product rule of differentiation. The expression 5t sine 4 pi t is the product of 2 functions, u equals 5t and v equals sine 4 pi t. Applying the product rule, d dt of uv equals u prime v plus uv prime, du dt equals 5, and dv dt equals 4 pi cosine 4 pi t. Therefore, I equals dq dt equals 5 sine 4 pi t plus 5t times 4 pi cosine 4 pi t equals 5 sine 4 pi t plus 20 pi t cosine 4 pi t milliamperes. Step 2. Substitute t equals 0.5 seconds. The argument becomes 4 pi times 0.5 equals 2 pi radians. Sine of 2 pi equals 0, and cosine of 2 pi equals 1. Therefore, I equals 5 times 0 plus 20 pi times 0.5 times 1 equals 10 pi milliamperes. The final answer is I equals 10 pi, approximately equals 31.42 milliamperes. This example demonstrates the application of calculus to circuit analysis. You should ensure that you are comfortable differentiating standard functions, polynomials, trigonometric functions, and exponential functions, as these are ubiquitous in electrical engineering. This worked example again applies the relationship I equals dq dt, this time to a charge expression that includes a constant term, a linear term, and an exponential term. The problem states, if Q equals 20 minus 15t minus 10e to the power of minus 3t millicoulombs, find the current at t equals 1.0 seconds. Step 1. Differentiate each term of Q with respect to t. The derivative of the constant 20 is 0. The derivative of minus 15t is minus 1/5. The derivative of minus 10e cubed is obtained using the chain rule. d dt of minus 10e to the power of minus 3t equals minus 10 times minus 3 e to the power of minus 3t equals plus 30 e to the power of minus 3t. Therefore, I equals dq dt equals minus 15 plus 30 e to the power of minus 3t milliamps. Step 2. Substitute t equals 1.0 seconds. I equals minus 15 plus 30 e to the power of minus 3. The value of e to the power of minus 3 equals 0.04979. Therefore, I equals minus 15 plus 30 times 0.04979 equals minus 15 plus $1.494 equals minus 13.506 milliamps. The final answer is I equals minus 13.506 milliamps. The negative sign of the current is significant. It indicates that at t equals 1 second, the charge is actually decreasing with time, meaning the current is flowing in the direction opposite to the assumed positive reference direction. This problem also demonstrates the use of the chain rule for differentiating exponential functions, an essential technique for analyzing circuits containing capacitors, inductors, and other reactive elements. This worked example applies the definition of voltage, also known as potential difference or electromotive force, to a practical circuit element, a light bulb. Voltage is defined as the energy transferred per unit charge. The formula is V equals delta W divided by delta Q, where V is the voltage in volts, delta W is the energy in joules, and delta Q is the charge in coulombs. The problem states an energy source forces a constant current of 2 amps through a light bulb for 10 seconds. During this time, 2.3 kilojoules of energy is given off as light and heat. Calculate the voltage drop across the bulb. Step 1. Find the total charge transferred. Using delta Q equals I times delta T, delta Q equals 2 amps times 10 seconds equals 20 C. Step 2. Convert the energy to joules. Delta W equals 2.3 kilojoules equals 2,300 joules. Step 3. Apply the voltage formula. V equals delta W divided by delta Q equals 2,300 joules divided by 20 C equals 115 volts. The final answer is V equals 115 volts. This result is the voltage drop across the bulb, the amount of electrical potential energy converted to light and heat per coulomb of charge passing through the bulb. Note that this is consistent with common domestic light bulb ratings, which typically operate at voltages between 110 volts and 240 volts, depending on the country. The relationship between voltage, energy, and charge is one of the most important in electrical engineering and underpins the concepts of power dissipation and circuit efficiency. This worked example deepens understanding of voltage by examining its sign, which carries important information about the direction of energy transfer. The voltage V sub AB is defined as the energy required to move a unit positive charge from point B to point A. Formally, V sub AB equals W divided by Q. The problem states moving charge Q from point B to point A requires 100 joules. Find versus sub AB for A, Q equals plus 5 coulombs, and B, Q equals minus 10 coulombs. The voltage formula is applied directly. V sub AB equals W divided by Q equals 100 joules divided by Q. Part A. Q equals plus 5 century. A positive charge is moved from B to A. Versus sub AB equals 100 fifths equals plus 20 volts. The positive result indicates that point A is at a higher electrical potential than point B. Energy is consumed in moving the positive charge from lower to higher potential, as in moving against an electric field. Part B. Q equals minus 10 century. A negative charge is moved from B to A, which is physically equivalent to moving a positive charge from A to B. Versus sub AB equals 100 divided by minus 10 equals minus 10 volts.
The negative result indicates that point A is at a lower electrical potential than point B. The answers are V sub AB equals plus 20 volts and B, V sub AB equals minus 10 volts. The sign of voltage is not merely a mathematical artifact, it carries physical meaning about the relative potentials of two nodes in a circuit. A thorough understanding of voltage polarity is essential for applying Kirchhoff's voltage law correctly in circuit analysis.